Okay, we've seen that you can have motion be going along the positive direction, for example, and then stop and reverse itself and then go in the negative direction, or vice versa. And these points where the motion stops are called turning points. And understanding how turning points work can be something that help us understand motion. And so I just wanted to do a quick explanation about turning points and work an example so that you can see how this can be applied to a real problem. So here is our graph of motion that we saw in a previous problem. And we can look at this graph and see that as the object moves, and this is one-dimensional motion again, there's a point where the object reverses itself. So here it's moving with a negative slope. The velocity is negative, it's going in the negative direction. But there's got to be a point right there where it momentarily stops. The velocity is 0. We know that the tangent is horizontal there. So that's the point where it reverses itself. And then again, we get to a point where the velocity is 0. And then there is that, again, reversal. These points where you have the reversal of motion, in calculus, if we were analyzing this function, we would say that those were critical points. But we can think of them just as turning points because what we're concerned about is the actual motion of the object. So here's an example we want to look at. We have x of t, which is the position of a particle as a function of time. So I plug in any time t, and that tells me what the position of the particle is at that time. And that function is given by -6 meters over a second squared times t squared plus 24 meters per second times t. And the question is, given that this is the function which describes the motion, so from here to there, this is our position function, we want to describe the motion, and we want to locate where any turning points are. Now, if you look at this function, you can see immediately that we have t squared, and we have t. This is parabolic, and the fact that there's a minus sign in front of the squared term, that tells us that the shape is going to be something like an inverted parabola. So that's something that is maybe evident to you. You might remember from your algebra or your calculus, but even if you didn't know that, you could simply plot the point. You could set up a truth table, t equals to 0, t equal to 1, t equal to 2, and just plot values of x and t and plot out the shape. Graph it by hand or graph it with a computer, and then you would be able to determine the shape of the motion. Here you can see that I've done a computer plot of this function, and there are a few things that we can note. First of all, we can see that there is a turning point right here at the top. And since we know this is parabolic, we would expect it to be symmetric. And it goes from 0 to 4. That's where the position is 0. So it starts at the position 0. It increases to the turning point, and then it decreases. And the place where it returns to 0 it looks to be at 4. So we might expect that the turning point to be in the middle at the time 2 seconds here. And this, by the way, is the time axis, and this would be the position axis, x of t. And so we can say that we expect the turning point to be at 2 seconds, and up here we can look over, and it looks to be at about 24 meters as the position. Now, solving it graphically, because of the symmetry involved with the parabola, we're pretty confident about our answer, but you won't always know if a function is symmetric like that, and so finding the turning points using a graph, there can be a lot of error there, a lot of uncertainty. We can actually calculate numerically the exact value for the turning point, because we know from calculus that anywhere there is a critical point, or in this case we're talking about a turning point, the derivative of that function equal to 0 locates the turning point. Remember, the derivative represents the slope of the tangent line to the curve. At the turning point, we expect that slope to be 0. So if we take the derivative of our function, this is our function here, if we take the derivative of that and set it equal to 0, that will let us solve for the time when the object turns around. and then we can take that time and plug it back into our position function, and that will give us the position where it turns around. So here we've done that. We've got the derivative of the position with respect to time is set to 0. And so taking the derivative, this was our position function that we want to take the derivative of. And so when you take the derivative of, you've got minus 6 meters per second squared times t squared, the 2 comes down, and that gives us minus 12 meters per second squared times t. And then the t here just goes away because when you take the derivative of t, it becomes 1, and that leaves us with 24 meters per second. So minus 12 meters per second squared t plus 24 meters per second equals to 0. Solve that for t, and I think you'll agree that you do in fact get t equals to 2 seconds as we expect. We can now take that time and plug it into our position function. X of 2 seconds is minus 6 meters per second squared times 2 quantity squared, and that gives us plus 24 times 2. So this multiplied together, we've got minus 6 times 4. That'll give us the second squared, and the second squareds will cancel, so that gives us minus 24 meters. And this is 24 times 2, so that gives us plus 48. Add those together, you end up with the x position at 2 seconds is 24 meters. And of course, we saw that from our graph. So our graphical solution worked perfectly fine in this case, but the numerical solution is very exact. And so if you're given a choice, the numerical solution is going to be the better way to go.